in a similar fashion with serial addition towards the full tree multiplier, which is the fastest we can bring. And then we talked a bit about this kind of truncated multiplication, which is very important, and about the fact that when you multiply integers, you really need twice dynamic range. But when you multiply fractional numbers, whatever you obtain is more precision beyond the unit in last position. And then you may decide to put effort in computing that or not. You can get at most 7 units in last position if you consider all the dots which are here after the separation line, because here it's your precision in normal representation, and you can do some kind of compensation. In practice, people are very much struggling for that, because if you look at the matrix, you actually drop half of the matrix. Then from the hardware point of view, you save a lot. And depending on how you do that, you may drop the dots completely, or you can do some kind of compensation. And in here you have 2 types of compensation. This is fixed compensation. Doesn't matter what I have here, I always add 4 units in last position. Or I do some kind of adaptive compensation, then I look at 2 bits of my operands, and those will give some kind of compensation here. In practice, there are a lot of proposals for that, and it's still a kind of research topic. Now, this is a very weird multiplier, because I told you we even go serial and slow, or we go towards a full tree in order to be fast. Now, this is a tree, but it's a kind of degenerated tree, because like I have here in this example, if I want to really go fast, I will group the operands per tree, and then I will put, them to work in parallel. What it's here, it's like a propagating kind of carry-save tree. You can see it as a tree, but the depth of the tree is not any longer logarithmic, it's linear in the number of operands, because you add 1 new partial product at a time. Now, what is happening in this one is that the critical path will be the delay of these carry save headers, which are cascaded, plus the delay of this ripple carry header to form the partial, the final product. Now, this may look very weird from the conceptual point of view, but there is a reasoning behind such an approach. And the reasoning was some time ago related to some issues, and we kind of discussed a bit last time. Then you could pipeline it, it was very regular. And today, things are getting even more important, because today wires are dominating the delay of the gates. And such a nice array has short wires, there are only local interconnects, and things, are working quite nice. Now, each cell here, it's essentially a full header and a gate, which is creating the partial product, the dot for that line. Now, you see that while I'm compressing the numbers, I'm producing for output some bits of the partial of the product, which we know in a normal tree that we do. And after this is done, we have a ripple carry header which is generating the rest of the bits. Then from 0 to P5, I can say they are generating via carry save addition, and 6 to 9 they are generating by ripple carry. Such an approach is very regular and is nicely to lay out, and one of the big reasons behind the nano era time was that such a structure was very good from the power consumption point of view. Now today we think about regularity also, and people are also trying, to make it go faster and to make it to work with 2's complement. In here you have 2 things which are added. One is about the 2's complement, and is this part in here, which is essentially taking care of the fact that the last bit of the multiplier has a negative weight. Then you do, all of them are doing addition, but this one is doing subtraction. You invert those guys, and then you have a hot carry injected in the calculation in order to do the 2's complement calculation. And there is something else which you see here, which is kind of weird. I can jump some of those blocks in order to make the design faster. And this is exactly what is suggested here. I can bring this output, not as to contribute in this reduction, but it can contribute here in this reduction. And then in this way, my critical path is slightly shorter. Then if you compare with this guy, the critical path was here in this way. Now this is slightly shorter. And because of the fact that it doesn't matter where I add the value, as long as I add it in a proper way, I can do that. The value is preserved. But you may also imagine, what about instead of doing from here, just jump directly to the end and make longer jumps. This is a very small array multiplier, but in a larger one, you may want to make more jumps. You already know why that will not be good. Or today is not a good day for science, right? If you look outside, I don't know how it is in Eindhoven and in Twente, but here is fantastic weather. Then if I jump over stages, I'm actually destroying the regularity. And I have longer wires. Then basically, I will not do that. I will keep the regular structure. And you see, it's a nice array of full adders which are equipped with an AND gate in order to generate the product for that location. And you repeat it, and you have a very nice compact layout. You broadcast the values of the two operands in horizontal and vertical way. Then this is a design which is taking into consideration more layout aspects than algorithmic aspects. I think this is good. And now you already can see that this is not a fast design. However, I can do some kind of things in order to make it faster. One of the things is to do calculation in a similar way with, based on a kind of anticipation. Then remember the carry select, where we computed the sum in the two situations, one if carry is 1 and the other if carry is 0. Then we anticipated the calculation. Now what we do is we combine this concept with the concept of the array. And in this way, you do not have to have a final ripple carry adder. While you progress in the calculation, you do speculation on the results, and eventually in the last moment, when you have, you arrive to what would have been here the corner, after going on the diagonal, you make the final selection. This will solve one part of the story, because what we'll do, I will still have to travel on this diagonal, but while I'm traveling on this diagonal, I keep on constructing the sums, or essentially is the product, in the two versions. And when I'm here, those bits will be selected in once because I computed them in both cases. Now, this will kind of destroy my regularity in a way, because I will not have that very beautiful structure. But it's not very bad. Would I try to do here directly a fast adder like a carry look ahead or something like that, the regularity will not look very well. In this way, I'm kind of extending, you know, each row with some anticipation. Then I still have a nice construct. And this is a solution which is utilized. Okay. Now, we already said that this kind of approach is good to be pipelined. And you can apply pipelining in many designs. And multipliers are very well for this pipelining concept. The problem with the pipelining is that you have to cut the design in the proper way. Then probably it's good to repeat that. Then if you have a functional unit, okay, which is this, then you have some inputs and you compute some outputs. This will take you a certain latency. Let's call this delta. If you want to do calculation faster, you have two solutions. One is to make this, you know, to work on the design, on the structure of the circuit, to allow the calculation to happen faster. That's one approach. And this is, you try to diminish the latency of the circuit. The other approach will be to make the assumption that you are dealing with back-to-back calculations, which means you have a pipe which is full of operands, and this is connected to the input, and then another one and another one will come, and you will have a lot of those. Now, if you have such a situation, latency is not that important any longer. Throughput is more important. And this is the principle of pipelining, and all processors, modern processors, rely on that. And what you do is you split the design in parts. I did it in 2 here, but you can do it in many parts. The more parts you have, the faster the design, because the latency, if you look at the design, will be actually larger, because here you have to put registers. Then latency will be this, plus the small delta, which is the overhead of the registers. However, after you fill the pipeline, you will get one new result each and every delay of this stage, which will be something like delta plus small delta over 4 in my case. Then I'm not speeding up 4 times, but it's almost 4 times. And I have a big time advantage if and only if I have enough operands to crunch. If not, this will be slower than my original design. Then pipelining as concept relies on the fact that it's busy all the time. Now, in this case, because you have an arithmetic unit, there are no problems like when you speak about the pipeline of a processor, where you execute an instruction stream and you may stop in the middle of the execution because you went in the wrong direction. But this is another phenomenon. Then in arithmetic units, the smaller this stage, the better. Then you can try to make this stage as small as possible, assuming that you have enough data coming. Now, this principle can be applied to multipliers, and then
the small delta wouldn't have to be divided by 4. It depends on how you define
because
delta.
in here delta is not exactly the overhead of a ledge.
The small delta is 4 registers delay.
Actually, it should be longer, right?
You can put it, you know, it's not that important, the calculation. It's the concept which is important. You can put it like that. If you want to be precise, it's in this way. But actually, it's not exactly like that. Because there are other phenomena inside which are contributing. Now, if I divide here by k, and k is large, I will get to a point where the flip-flop will dominate the calculation, and then it's not a good solution. I have to have a good balance between the activity that I have in the stage and the overhead coming from the flip-flop. Because, you know, at the extreme case, I can put here only one gate and then a flip-flop. And I will run at, I don't know, 10 gigahertz frequency, but I will not really do much calculation. And this will not be also a very good solution because high frequency clock means high energy. Now, this is a concept which is applied to multipliers based on the assumption that you have more than one multiplication active in the processor, and then it will be good to put them back to back. Now, when you do that, you have to be careful where you do the cuts. And you see, here it's one. This is an interesting drawing, and this is telling you something about where to re-inject, you know, your partial value, because you are keep on accumulating, and you can inject it also here at the beginning, but that will not be a good idea. You will delay the production of the result. Now, array multipliers are very, very good for pipelining. You see, we have a lot of registers, and essentially speaking, if you want to run a very, very high frequency, you can run at the frequency which is determined by the deladder of a full adder plus something, which is very fast. Unfortunately, this is not exactly a feasible solution. You will spend too much energy in the clock. And except if you are in an environment where you do heavy digital signal processing, and in that case, such a solution is good, because what you will do is you will create a number of multipliers, bunch of them, array multipliers, because they are small, regular, and they have very high throughput, and you will feed them all with your application. And due to the pipelining, they will be very effective. Now, in this design, if you look at it, it's actually split in 3 stages. A very important aspect of splitting is to balance the parts, because the longest part will determine the cycle time. And unfortunately, in most of the designs, you cannot do that let's say, precise cut. In here, because stages are dominated by full adders, it's simple to do a nice cut. But in another design, think about, I don't know, a prefix adder, there is still okay. But if you think about the processor, in the pipeline of the processor, different stages take different time. And then it's very hard to balance them right, which means you will run the processor with a clock frequency which will give you some slack. Let's say in this stage where I am, you know, faster, I have the results ready here, but I will just read them a bit later, because the longest stage will determine the clock frequency. Okay. Now, as usual, we have solutions which are going a bit beyond the standard solutions, and one of the approach is to apply divided interval. If you look at this design, what is the approach here is to say, okay, I'm dividing my operands in half, and I will process each half like being a large digit. Then it is like a high radix multiplication. But AL and A high can be actually 16-bit operands if I'm doing 32-bit multiplication. And this is bringing me to the idea of applying in a hierarchical way multiplication, and I'm doing the following. I'm saying I have to compute the product of those guys. If this would have been a bit, I would have done exactly the same. This times this and this times this would come here, right? And then this times this and this would come here, okay? Now this is not a bit. This is a digit. It's a very large number. And what I'll do is I will use 4 multipliers, which in my case are, you know, these are, how many bits are here? B bits, okay. Why B and not N? Who knows? Then this is a B bit number. Then I will multiply this with this, and I will write the product. I will multiply this with this, and I will write the product. I will multiply this with this, and I will write the product. And this with this, and I will write the product. Each product, it's a 2-bit number. I need 4 multipliers, but my multipliers are not 2-bit multipliers, are half of that. And they can work in parallel. Then the calculation of this, and this can be done in parallel. Now what I have is I have to reduce those numbers to my final product. Because of the nature of the multiplication, this half is going out. It's already ready. For the rest, I have to do something. And there is a big time advantage here because I can put them in this way, which already let me think about 3-to-2 reduction. Then what I did is I make a big multiplication with 4 multipliers, which are half capacity. I need to do a 3-to-2 reduction on this side, and then a final addition. And I can apply that in a hierarchic manner. I can also design, you know, those multipliers in the same way. Now it's not B, it's B over 2. And the question is, why would I do that? Just because I want to make your life difficult? Do you see a kind of philosophy behind doing that? Come on, guys. I know it's not a good day today. Neither for me. We have to work together. Sorry?
The 3 for the summation is less D.
The 3 for the summation, what's that? No, why would I try to do this kind of hierarchic approach? That's my question. Where will be the benefit?
You can split the problem into blocks, which are very similar layout.
There is a kind of regularization of the layout, but there is also a price, right? And I have a time penalty, I have an area penalty, which eventually come to the picture, but I have that kind of prefabricated building blocks, which I can use. Let's say I'm doing business with an FPGA, and in FPGAs, you know, there are 9-bit multipliers, which are prefabricated. And you can use those together to build a larger multiplier in this way. Okay? Now, you may not say that, and the synthesis tool will do that anyway. But that's the idea. You have prefabricated building blocks, and you use them in order to make some kind of hierarchical approach. And divide et impera, it's usually a solution when we cannot deal with the complexity of the problem. Now, if I apply that, you know, I split in more parts, then if my operands are larger, this compression will look something like that, and you see it will go taller and taller and taller, which means I keep the dimension of the multiplier the same, but I will have more of them because my operands are larger. I will have more than 3 rows after the multiplication, the first multiplication, which means that I will have now a tree of full adders, which will reduce me this to 2, and then I will have a final addition. Okay, you can also do it in a non-uniform way, but this is more like, you know, an intellectual challenge. Most of the time in practice, your operands are nicely balanced. They do not have different dimensions. But if they do, and you want to save, you may arrive in such a structure which will make your life a bit more complicated. Now, this is the way such an approach will look if I look now at the circuit. Then what I have 4 multipliers, which are now, you know, then I'm building a 16-bit multiplier. Then on the first level, I am multiplying all of them. Then the delay, it's the delay of a 4-bit multiplier. And then I will have to go on the critical path of this addition tree, which is trying to then I'm not doing reduction, I'm just doing addition and I'm propagating the carry. And I can have a bit of parallelism. Then at the beginning, you know, I do that addition, then I can do 2 in parallel, and then I can do this addition and 1 addition, and I'm done. This is kind of slow as a design because I'm not taking advantage of the fact that in here I could do some compression, 3 to 2 compression, that is not based on carry save addition in this part. However, if I do carry save addition in this part, I would have to face a final ladder which is wider and to propagate it all over the place. Then this is a kind of compromise which is propagating carries in steps. And there is something else, which is nice about this solution. All my blocks are 4-bit blocks. Then I deal with 4-bit multipliers and 4-bit adders. Then if I have 4-bit multipliers and 4-bit adders, I can build, you know, 16-bit multipliers and 16-bit adders. And then I can apply it again upwards, and I can build, I don't know, 64-bit and stuff like this. Then it is nicely regular. Okay, this is an interesting thing, but it's a bit outside of the scope of the discussion on multiplication. I don't know, I didn't check, probably it's in the new edition of the book. This was proposed by Karatsuba, and he essentially tried to diminish the number of multiplication in such an approach. Then remember, we had 4 multiplications, which are going in parallel, and then 5 additions. Now Karatsuba rewrote this equation, and he obtained 3 multiplications and some more additions. This is a trick which is utilized in cryptography, and wherever you have huge operands, then when you have huge operands, then you rely on a library in order to do that kind of multiplication. And if you do Karatsuba's approach, you can win a lot. But in hardware, it's not, I mean, as far as I know, it's not a way to implement things. But, you know, this is a nice example that when you play with formulas, simple arithmetical manipulations can save you hardware or computation time. Okay, it was, you know, this idea of doing things in a hierarchical way was nice. But somehow I had a problem. You know, I was mixing blocks which were 4-bit blocks, but they were different kind of specialized blocks. And a 4-bit multiplier is not like a 4-bit adder. it would have been nice to have something which is only one type of block, to replicate that block a number of times, and then to get your solution. That would have been a nicer hierarchical approach, not based on one type only, okay? And this is the key behind such a unified hierarchical approach. Then you rely on a building block which is doing a compound calculation. It's doing a multiplication and two additions in the same time. That they can be of any kind of dimension of operands. You can scale them. But in our case, we have a building block which is doing a multiplication of two operands. One is 4-bit, the other one is 2-bit. And there are two other operands. One is 4-bit operand and the other one is 2-bit operand. Then practically, this is the formula that I'm computing. P, it's ax plus y plus z. I know the dimension in bits of those guys. And what I want is I want to design the circuit which is doing that. The first step will be to create the dot diagram. Then y, it's 4-bit. I put it here. Z, it's 2-bit. I put it here. I also have to compute the product, which is ax. A is 4-bit. X is 2-bit. Then this represents the x product. Now, my goal is to do the implementation. It's simple. We know the ingredients. I see 3 dots, I put a full adder. Then I am doing a reduction first. It's like a carry save adder. I generate already 1 bit for output, and here I have a 4-bit adder because I can also use the carry in. And I can design blocks like that for any type of dimension. Now, the strange relation between the operand width relates to the way we are utilizing them. And this is a way to implement now a larger multiplication with that type of building blocks. And now you see, I only have them. And, you know, both sides of the slide are telling the same story, but it's told in different ways. If I look in this column, I see the partial product matrix for the 8 by 8-bit multiplication. In here, I have the dot representation of my basic building block. And what I should try to do is I should try to make a match between this and whatever I have there. Then to try to cover, to eat from those dots as much as I can in order to arrive to a result, which is now not a 2 numbers, it's just my final result. Then I am making a trick which is similar with applying full adders, but is with a different shape. And as you see, in the first moment, remember I have propagation in this guy. Then I have to be careful not to create some problems in the structure. Then in the first moment, I take only that part, which are 8 dots, which are essentially the result of the product, AX. If I think at such a multiply add module, which is computing AX plus Y plus Z, I assume that Z and Y are 0, and then I'm just doing the multiplication of those. Then you see, I take 2 bits and 4 bits from each of the operands. I take 2 bits from the multiplier and 4 bits from A. Now this will give me 6 bullets for output. 2 of them are already free, but the next can contribute. And now I'll do the same. I'll try to cover as many bullets as I can with my, you know, it's like pattern matching, if you want. And I would look first on the possibility to use some additive inputs. And I can use the 4 red bullets, like the 4-bit additive input to my module, and then 2 more bits from X. In the same time, nobody is stopping me of using another module in parallel to process the most significant part of A with the previous 2 bits of X. Then practically, as opposed to the previous time when I said my operands are like that and I split them in 2 equal parts, now I have this in 4 parts and this in 2 parts. Then I compute this time this time this, and so forth and so on. But in top of computing the multiplication, I'm also accumulating intermediate results. Then I did this, and now I have 2 modules which are producing output. I see them again in red, 2 bits are for output, and now I arrive to the moment when I'm really using the full capacity of my module. This is the product, this is the additive input on 2 bits, on 4 bits, and this is on 2 bits. And then on this one, I just have the additive input on 4 bits. Then I apply again 2 of those. Again, I'm out. Full. There is nothing I can do here. Then result, again, and I'm done. Now, if I just look at the dots and I'm not thinking of what I'm doing here in this way, I may get trapped and try to over compress the dots. But that may bring me to a wrong approach. Because you see, I was very much lucky here in the last moment. I had, you know, full capacity. I'm really using that in the proper way. If I am doing some other compression here, I may damage the structure. Then from one point of view, this is a very nice approach. From the other point of view, you can look at this one and think in the way that I just said, right? Then I'm starting with X. This is the least significant part of X, and I'm multiplying with this, okay? And this is this module, which is providing me some output and some kind of input to the next stage, where I am multiplying the next part of X with the least significant part of A. I'm producing 4 output, but I'm also accumulating from the previous calculation. And then I look now at the next stage of X. I'm again multiplying with the least significant part of A. I'm producing 4 output. I'm accumulating from this, but I'm also accumulating things which are coming from the most significant part of A. Because in this column, I'm doing those guys, you know, which they belong to the most significant part of A. Now, one way or another, I should be able to arrive to the solution. And the solution now is very regular in the sense that I have only one type of module, and I am processing all the bits. If you get at the exam such a question, which you might, I don't know, be sure that you are processing all the bits and then you are adding them in a proper way. Then some people do have better time with this, other with the other one. I don't care which the one you use as long as you explain it in a proper way. In here you actually follow the conceptual evolution of the calculation. In here you are just trying to do pattern matching. But the pattern matching is related to the way you process the numbers. Then practically such an approach, it's better than the previous one. It's very regular, I'm using the same kind of building block, and it's scalable, and it's, you know, it's nicer. If I make those blocks larger, I can process larger operands in the same kind of delay. There is, as always, a kind of trade-off between how large these blocks can be done and what is the performance of the larger multiplier. Okay? Break time.